All right, good morning again, everyone. So today tatapusin na natin yung unit number 2 ng Math 175. So that means next week I will release the questions for the second problem set. And I think last time I already mentioned the dates. So wala na nga lang yun sa copy ko na ngayon ng modules. So just take a look at it. So I'll make the appropriate announcements pag ready na yung problem set number 2. You will have probably 1 week to finish it. So kindly watch out for it. Wala tayong lab extra on Monday kasi holiday yung Monday. I think Malacanang finally declared it a non-working holiday. So wala tayong extra, but watch out for the problem set for next week. Now that's also coincided with sort of the free laboratory session kasi I promised na for module number 9 we will not have a laboratory exercise. That's why I changed Lab Extra 4.1 to Lab Extra 4 para full 50 points yung makukuha niyo sa Lab Extra na yon. So kindly work on it. The deadline is later tonight. So ngayon, ipagpatuloy lang natin yung discussion natin about my concluding thoughts about linear systems or solving linear systems. Last time, we looked at the concept of the pseudo-inverse, the Moore-Penrose pseudo-inverse, which provides a way for us to compute a solution, at least the least square solution to rectangular systems, all right? Kasi sabi natin, kapag meron kang rectangular system, either it's consistent or inconsistent. Kung inconsistent, wala ka talagang solution na mahahanap at all. So the next best thing that we can get is a least square solution, something that will minimize the L2 norm of the residual. Pag sinabi nating residual, halimbawa meron kang solution na x star, yung residual ay ax star minus b. Alright? Gaano kalayo yung nakuha mo na a times the solution vector minus the right-hand side. And we want this to be very close to the zero vector, right? So i-measure natin to according to some norm, all right? So ito yung kinukuha natin. Kapag inconsistent yung system, we want to see, okay, meron ba, ano yung pinakamagandang solution na makukuha ko with respect to the size of the residual? So gusto mo yung si X star na makakapag-minimize ng quantity na to. And luckily, if we will measure this norm with respect to the L2 norm, all right? So makukuha natin yung tinatawag nating least square solution. And the least square solution is obtained by computing the solutions of the normal equation. So nagsimula ka halimbawa sa inconsistent na ax equals b, all right? Tapos ang gagawin mo lang para makuha yung normal equation, you multiply both sides by the conjugate transpose of the matrix A. So left multiplication yung gagawin, you get this one. And then we are hoping that even if A is not invertible, we're hoping that A conjugate A will be invertible. Okay? And that is often the case. Kasi and actually this will even work even if A is not square. Because if A is of dimensions m by n, yung A conjugate, kasi ang A conjugate lang naman ay yung matrix na ang laman niya ay yung conjugate ng mga transpose ng matrix A. Ito ay magiging n by m. So their product will be n by n. All right? And pwede tayong mag-usap about the actual inverse. And actually, the solution to the normal equation, which we usually refer to as the normal solution, is given by this guy. And this formula coincides with, or a substantial part of this formula coincides with the Moore-Penrose pseudo-inverse. So itong multiplier nito, ito yung tinatawag natin na A plus o yung Moore-Penrose pseudo-inverse, provided that A conjugate A is invertible. Okay? Tapos meron pa tayong isang case na pinakita last time. Kung ano naman yung gagawin kapag hindi invertible yung A star A. Ang pwede mong tingnan, invertible ba si A star? Because if A star is invertible, even if A star A is not invertible, then you can still find the Moore-Penrose pseudo-inverse. Unfortunately, for the other cases na parehas hindi invertible si A star A at saka si A star, meron pa rin yung Moore pseudo-inverse, okay? Yun nga lang, hindi ko na ipapakita kung paano siya kinocompute. Though you have the four properties that it should satisfy dun sa definition ng Moore-Penrose pseudo-inverse. Tapos may theorem tayo na nagsasabi kahit ano pang matrix yan. lagi siyang may more Penrose pseudo-inverse. Pero limitado tayo sa 175 because I don't have time to teach you the entire theory about pseudo-inverses. Ano? So, limitado tayo dun sa mga cases kung saan invertible si A star A o kaya si A star. And I think we finished with this example last time. I presented this earlier nga ba? Oh, actually, hindi pala. First time nating nakita tong example 9.2 rito. Ito ay nakita natin to be consistent because we found an exact solution. So yung kagandahan ng least square solution ay kapag yung original system ay may solution, yung least square solution na makukuha natin using this formula will coincide with the exact solution. Kasi nga madali yung maisip kasi ang promise ng normal equation, makukuha natin yung minimizer netong functional na ito, ng L2 norm na ito. And this will be minimal kapag meron kang actual solution or exact solution, the minimum value of this guy will be 0. Okay? Tapos, yun yung makukuha natin mula sa pag-multiply ng pseudo-inverse ni A with B. And that's what happened with this example. Okay? 1-1 transpose yung nakuha natin. Nalaman ko na siya ay exact solution, na hindi lamang siya least square solution, pero isa siyang exact solution because the residual has a 0 norm. Kasi yung AX star ay equal mismo dun sa right-hand side. So we got the best case scenario. And actually, that's the beauty of the pseudo-inverse kasi generalization siya ng konsepto ng inverse. So maraming properties ang involved. And with these properties, kaya usually yung mga computing softwares like MATLAB, instead na ang kino-compute nila yung inverse, ang kino-compute nila ay yung pseudo-inverse. Pagka nagpa-compute ka kay MATLAB ng linear system, by default, pag hindi mo sinabi or hindi mo in-specify na matrix inverse mismo yung gamitin mo, ang gagamitin niya ay yung pseudo-inverse. Kasi mas madaling mag-compute ng pseudo-inverse kaysa sa actual inverse. Okay? Now, Ezekiel has a question in the chat. What if hindi invertible si A star A, but yung A star yung invertible? Yes, we have the formula for that, Ezekiel. Let me scroll up. Sana hindi ko nakalimutang isulat. I think I wrote that here somewhere. Should be here. Or nakalimutan ko. Hold on. Ayan, nasa theorem 9.2. Okay? So, kapag kasi A star A invertible, you'll use this formula for the pseudo-inverse. Kapag ka naman si A star yung invertible, ito yung gagamitin nyo. Okay? Pero actually, rare ako nakaka-encounter ng times na hindi invertible yung A star A. Usually in applications, madalas invertible yung A star A. Okay. Tapos mas natural kasi yung itong formula na to involving the inverse of A star A kasi siya nga yung nanggagaling sa normal equation. Ano? So, yeah. Oh, you're good, Ezekiel. Hold on. Excuse me for a minute. Okay. Tapos ang isa pang kagandahan nung teorya natin about pseudo-inverses, merong paraan para makuha natin lahat ng posibleng solution kapag consistent yung ating linear system. Kasi, okay, kapag inconsistent siya, makukuha natin yung least square solution. Pero kapag consistent yung system, lalo na kung rectangular yan, kapag consistent yung system pero square, isa lamang yung solution. There will be an exact solution. However, if you have a consistent rectangular system, posibleng maraming solutions ang mag-exist. Now, the beauty about the use of the Moore-Penrose pseudo-inverse, we can find all the possible solutions, and that's what we discussed in example 9.3 last time. So, yung sumunod na example, in-illustrate ko lang yan. Balikan natin to. Sa example 9.3, okay? Pinareconsider ko itong linear system na to. So, and we noted earlier that this is underdetermined. Pero siya ay consistent. there would be infinitely many solutions. In fact, I told you without proof that the solutions or any solution will be of the form -1 minus x2 comma x2 comma 2, where x2 is a free variable. So actually, makukompute mo yan by using elimination. Makukuha mo yung formula sa x1, sa x2, and then makikita mo na si x2 ay free variable, tapos si x3 ay equal kay 2. Alright? Now, tingnan natin kung paano natin magagamit yung equation 9.3 para ma-verify na indeed, infinitely many solutions siya, tapos ganito dapat yung form. Okay? Now, so, pwede natin computein yung pseudo-inverse, alright, para magamit yung formula 9.3. So, this is our coefficient matrix. This is 2 by 3, okay? So, computing ko yung A star A and hope that this is invertible. So carry out the multiplication, you'll get this 3 by 3 matrix. And since you have a square matrix, you can test for invertibility. Okay. So 120 at saka sa 105 tuturuan kayo paano mag-test ng invertibility. Of course, I think the easiest is compute the determinant of this guy. If the determinant is not 0, then it is invertible. Now, it is actually or actually hindi pala to invertible. Sorry. Ito yung isang case na hindi invertible yung A star A. Alright? Singular pala siya. So, hindi to invertible. Actually, obvious pala na hindi siya invertible kasi parehas yung first at saka second rows. So, hindi linearly independent yung rows. So, ibig sabihin, siya ay singular. So, hindi ko pwedeng magamit yung A star A o yung normal equations para ma-compute yung pseudo-inverse. Okay? So, ngayon, itetest ko, okay, kung hindi siya nag-work, tingnan ko yung AA star. Okay. So pag kinumpute mo yung AA star, ito yung makukuha mo, it's gonna be a 2 by 2 matrix. Tapos compute mo yung determinant ng 2 by 2 matrix. This would be 18 minus 16, so that's equal to 2, not equal to 0, then this is invertible. Ang kagandahan, 2 by 2 lang yan, meron tayong straightforward formula para ma-compute yung inverse ng isang 2 by 2 matrix. It's gonna be 1 over the determinant. Tapos pagbabaligtarin mo yung diagonal entries, so yung 3 at saka 6 na flip, tapos inegate mo lang yung kabilang diagonal. Ano? So yun yung pagkuha ng inverse ng isang 2 by 2 matrix. And here we'll see that AA star inverse is this guy. Okay? And then we'll use theorem 9.2 to compute the pseudo-inverse. So we'll use this formula. Tapos ang pseudo-inverse niya raw ay etong matrix na to. Okay? And then from our discussions above, the least square solution will be given by A pseudo-inverse or A plus times B. So this is our computed pseudo-inverse. Multiply it by the right-hand side vector. And we'll get the solution -1/2, -1/2, comma 2. All right? And if you plug it, if you compute for the residual, all right, kukomputin natin yung residual para makita kung ito nga ba ay least square solution lamang o isa itong exact solution. Well, we just need to multiply AX star and compare what we'll get to the right-hand side. But doing so, AX star will be equal to 1, 3, which is exactly the right-hand side B. So we got an exact solution. Dahil nakakuha tayo ng isang exact solution, ibig sabihin consistent yung system. Dahil consistent sa system, alam natin by equation 9.3 na lahat ng solutions nitong equation na to ay masusulat in the form in equation 9.6. Okay? Now, we will know that there will be infinitely many solutions because if you multiply A plus times A, yung pseudo-inverse times A, ang makukuha natin ay hindi equal kay identity matrix. Pag ito ay naging equal kay identity matrix, then this whole factor will be the zero vector. So ibig sabihin, unique yung solution na makukuha natin. Katulad ng nasa previous example. Pero rito, sa example natin ngayon, yung A plus times A ay hindi identity. In fact, it will be what? Sayang, diniretso ko na pala yung subtraction, ano? Pero hindi siya equal sa identity matrix. Pero, okay, so ibig sabihin, infinitely many solution, and then this will work for any 3 by 1 vector. So, mag-plug in lang ako dyan ng arbitrary vector W. Tawagin kong W1, W2, and W3, yung entries ng vector. This will represent any three vector of real numbers. So, this is the particular solution that we got. Ito yung A pseudo-inverse B na nakuha natin kanina, which we know to be an exact solution. Then this is the 3 by 3 identity matrix times A plus A. All right? Or A plus times A. Tapos makikita natin ito ay hindi zero vector or hindi zero matrix at makukuha natin ay etong guy na ito. And then you perform the calculations, you'll end up with this guy. Okay? Tapos ang mapapansin natin dito ay what? Kung ililet ko si x2, kung ililet ko itong pangalawang entry, ito yung x2 natin. Alright, kung ito yung tatawagin kong x2, it is easy to see that x1 is -1 minus x2. Alright, so kasi magkamukha sila, if we take their sum will just be equal to 1. So kung ito si x1, ito si x2, so we'll see that x1 plus x2 ay equal kay, tama ba? 0, 0, equal kay -1. So that means x1 can be written as -1 minus x2, right? So yun yung nakuha ko rito, which is exactly what we predicted or what I gave you in the introduction to the course, to the module. Okay? So ito yung paraan ng pagkuha ng lahat ng solution sa isang consistent rectangular system using the results we have for the pseudo-inverse. Okay? So any questions about that? Okay pa naman kayo? Okay, so the last topic I want to share with you with this unit is the use of the L curve. Ito kasi kailangan natin, especially if we're working with inverse problems. Ano? So meron kasing mga linear systems na napaka ill-conditioned ng coefficient matrix. Ill-conditioned in the manner that a very small change in the right-hand side will drastically change the solution vector x. Kasi ang ideal ay ang ideal scenario ay kapag binago natin ng kaunti yung right-hand side. Okay? Halimbawa, yung right-hand side ay nabago. Say, because in most applications, pag nag-solve ka ng system na AX equals B, ang gusto nating makita, ano yung input X dun sa process o dun sa system para makuha natin yung output na B. Alright? So that's the idea of solving AX equals B. What was the input that produced the output B? Now, in practical scenarios, the output vector B is usually from measurements. Galing yan sa isang data. All right, or actually, these are physical data that were either obtained via measurements or are expected to have been contaminated with noise. Halimbawa, yung right-hand side mo ay measure ng vibration ng isang object. Okay? So, kailangan mong i-measure yung vibration ng isang object through time. Kaya lang, ang mga measuring devices natin ay may inherent error involved. Walang perfect na measuring device. So, ibig sabihin, yung makukompute mo na system, supposedly ay AX equals B, posibleng hindi ito yung mabigay sa'yo na system. Na actually, ang mabubuo mong system ay AX equals B plus some measurement error epsilon, where epsilon is small. Say it's about 2%, 1%, 3% error. Now, ideally, we want the solution to this equation, tawagin natin itong double star. Gusto natin yung solution kay double star ay malapit dun sa solution kay star. Because we want the desired output, we want the desired input to the system to be close enough dun sa ma-reconstruct natin o mako-compute natin na solution. Kasi kapag ka yung x star o yung solution nito ay masyadong malayo dun sa solution ng AX equals B, then we are not guaranteed to get the same effect as what we would have wanted. Ang isang particular example dun sa research kong ginagawa, halimbawa, meron akong, bias ako sa research ko, yun yung mabibigay ko sa inyo na practical example. Halimbawa, meron ako ditong speaker. Okay. Tapos meron ako ditong Halimbawa, nasa room ako, yung classroom. Okay. Tapos, halimbawa, gusto ko rito, sa region na to, nagple-play, halimbawa, K-pop music, yung nandyan. Tapos dito, nagple-play yung P-pop. Tapos, halimbawa, dito, gusto ko ay quiet dito. Okay. So, ang idea ay, paano ko dapat i-design yung speaker o ano yung sound na i-blast ng speaker all throughout the room para yung mga tao dito sa region na to, P-pop yung maririnig. Yung mga tao dito, K-pop yung maririnig. Yung mga tao dito, walang maririnig at all. Alright? So, yung system na to ay, nagko-compute ako ng input para dun sa speaker. So, hinahanap ko yung input sa speaker X such that, okay, ang pag in-input ko siya dun sa process at yung process ay represented by the matrix X, makukuha ko yung output B. Yung output B ay vector consisting of the data that I want to match. It would be consisting of the data corresponding to K-pop, P-pop, and dun sa quiet zone. So yun yung right-hand side vector B. So isolve ko tong system na to, makukuha ko si X equals A pseudo-inverse times B. Yun yung makukuha kong least square solution. Now, ang idea ay, okay, pag ganito yung process, okay lang. Pero pag halimbawa, meron akong i-design na noise cancelling earphone. So, kung noise cancelling earphone yan, ang dapat mangyari ay ganito. So, halimbawa, ito yung anti-noise cancelling, ito yung active noise cancelling headphone. Tapos, halimbawa, ito yung ear. So, halimbawa, ito yung ear. O, yan yung earpiece. Ano? So, ang gagawin nitong active noise cancelling earphone, parang baligtad yung drawing ko. Lagay ko nga to dito. Yan. Tapos ito yung ear. Kunwari yan yung ear. So, ang mangyayari dyan ay yung active noise cancelling mechanism ay i-measure muna yung incoming noise. So, i-measure niya yung incoming noise. Ito supposedly yung magiging right-hand side vector B ko. Or yung negative niya, yung magiging right-hand side vector ko para alam ni active noise cancelling earphone kung ano dapat yung i-produce niyang sound para manigate o ma-zero out yung epekto ng noise papasok dun sa ear. Okay? So kailangan mahanap ko yung output B such that AX would be equal to negative B. Para yung B na noise pag nag-add dun sa sound wave na iproproduce ng speaker dun sa aking active noise cancelling headphone ay equal kay kay negative B. Pag sila ay nag-add, B plus negative B magzi-zero out. Walang noise na darating dun sa ear. Okay? Kaya lang dahil merong measuring component ito, so hindi posible na eksaktong B yung ma-detect ng active noise cancelling mechanism. So probably it will measure negative B plus epsilon. And pagka ill-conditioned yung matrix, yung solution nito ay posibleng napakalayo dun sa solution nung AX equals B. At pag nagkataon na yon, kapag ka ang feed ko dun sa aking active noise, dun sa microphone, dun sa aking ANC, alright, posibleng yung ma-produce ko na sound ay hindi negative B. Kasi para ma-cancel ito, dapat may negative B ito. Okay. So, yung solution dito ay posibleng malayo dun sa solution dito. So yung input ko na X na nanggaling dito sa system na may noise o may measurement error, okay, ay posibleng hindi eksaktong yung kailangan kong input para ma-cancel yung eksaktong noise. So ibig sabihin, there might be some part of the noise that can penetrate through my headphone. Yun yung problema kapag ka ill-conditioned yung problem. Okay? So, masyadong malayo yung makukuha mong solution from the ideal solution. So, the question now is, for a numerical analyst, paano ko dapat i-handle itong mga ill-conditioned matrices? Bababayaan na lang ba natin yan? Or can we do something about it? Okay? And luckily, we can do something about it. So, whenever we expect the right-hand side of our linear system to be perturbed by noise or to be affected by measurement error, okay, we want to guard against it, lalo na kung ill-conditioned yung system, which is actually almost always the case kapag ka inverse problem yung sinusolve nyo. And pagka inverse problem yung sinosolve, usually rectangular system then overdetermined yung mga systems na ating sinosolve. Okay? So, merong ang kagandahan ay may isang method that that does those two things simultaneously. Okay? Una, tinatry niyang magkaroon ng accurate solution with respect to the L2 norm. At pangalawa, nami-mitigate niya yung epekto ng measurement error o nung data noise doon sa solution. I mean, it tries its best to do or to make the solution from the perturbed system very, very close to the solution of the baseline or the ideal system. At yun yung tinatawag na Tikhonov Regularization Scheme plus the L-curve. Okay? So yun yung titingnan natin ngayon. Hopefully matapos ko siya. Alright? So yun yung sinabi ko dyan. Okay. So ito yung ideal goal natin. Gusto ko yung yung solution mula dun sa perturbed system, dun sa system that is contaminated by noise. Tawagin natin siyang X tilde, ay malapit dun sa solution nung walang noise, which is X star. So we want the norm of X tilde minus X star to be very, very small. Alright? Yun yung ibig sabihin ng double less than. So it is much, much smaller than the value 1. Okay? So, pero before that, kailangan nating i-quantify kailan nagiging ill-conditioned ang isang matrix para alam natin kailan ko kailangan gumamit ng fancy technique na tinatawag nating Tikhonov routine. All right? So, one measure for it is the condition number of the matrix. Now, the condition number of the matrix is commonly measured as the product between its operator norm and the operator norm of its pseudo-inverse. And we will denote the condition number of a matrix A by kappa. Okay? So kay MATLAB, kaya itong computein. Kino-compute ni MATLAB yung condition number using cond of A. Alright? Ang ginagamit niya dito ay yung L2 norm. Kinukuha niya yung L2 norm ng matrix A times the L2 norm of its pseudo-inverse. And that's the value of kappa. The bigger kappa is, pangit ako magsulat ng kappa. Hindi ako marunong magsulat ng kappa. So mukha siyang letter K pero kappa yan. So the bigger kappa is, the more sensitive the solution is with respect to perturbations in the right-hand side. But how do we know that kappa is big? Ganito na lang yung isipin nyo. Si kappa kasi yung proportionality o siya yung asymptotic bound. Hindi pala asymptotic bound. Siya yung scaling factor para sa isang upper bound dun sa relative error between the two solutions. Okay? So if you measure the relative error from the solution from the perturbed system versus the solution of the baseline system, okay? Yon ay laging bounded above by the condition number times the size of the noise with respect to the size of the right-hand side. So you can think of it as the percentage noise. Tapos ito naman yung percent change sa solution. So yung percentage change sa solution ay bounded above by kappa or the condition number times the size of the relative size of the error. Sorry, not the error, but the noise with respect to the right-hand side vector. Okay? So kapag of course, pag maliit ito, you can afford a big kappa. But if this is large, then you cannot afford a big kappa. So usually depende sa isang problem kung gaano kalaki yung i-allow mo na condition number. Halimbawa, in-expect mo na yung measurement error mo ay 5%. Yung precision ng measuring device mo ay plus or minus 5% yung margin of error. So 5% yan. So you can afford kappa, say, to be around what? Kappa could be equal to 1. Because if kappa is equal to 1, then you know that the relative difference between the actual solution and the perturbed solution will be at most 5%. Pwede ka pa nga mag-2 kung afford mo na 10% yung relative change doon sa solution ng perturbed saka baseline system. Okay? But usually, kappa is in the hundreds if not thousands. So yun yung problema. So tingnan natin, example 9.4. So ito yung matrix na sinolve natin kanina. Ito yung consistent system na merong infinitely many solutions of the form -1 minus x2, x2, comma 2. Alright? Kaya lang, pag kinumpute mo yung condition number niya, it's around 630 na napakalaki. So this is quite big because that means that the relative change in the solution that you will obtain will be 600 times or 630 times the size of the noise. So if your noise is about 1%, tapos ito ay 629, so that means the solution that you'll get or the relative error is around 600% dun sa actual versus the perturbed solution. So prepare to get 6 times the error dun sa actual solution. All right? Or at most, upper bound eto. And true enough, so tingnan natin. Okay, totoo ba? Ganun nga ba yung nangyari? Kunwari, meron tayong noise na epsilon na 0.01, negative 0.032, at saka 0.01 dun sa right-hand side. So ibig sabihin yung mga right-hand side elements mababago lang or mapaperturb by this respective values. Okay? So made up values lang to. Usually random vector yung epsilon kasi sila yung noise. Usually Gaussian noise or whatever random number you want to you generate of the appropriate size. Okay? So pag ito yung kinonsider ko na epsilon, ang size ni epsilon relative to the right-hand side vector ay around 1%. So it's 1.05%. Yan yung measurement noise natin. So dahil yan yung measurement noise na yan, kapag ka sinolve ko yung perturb equation, yung equation 9.10, ang makukuha kong solution ay ito. Okay? And I expect this to be around what? 1.05% times 620 yung relative error niya from the baseline solution. Okay? And true enough, this solution we obtained by using the least squares method or by using the pseudo inverse. So that means x tilde is equal to a pseudo inverse times b plus epsilon. Ito yung nakuha kong solution. Actually, maganda tong solution na to kasi pag kinuha ko yung residual o yung relative residual, 0.56% lang. So that's even less than 1%. So everything seems well. Maganda yung nakuha kong solution mula dun sa least squares, mula dun sa pseudo inverse. Kaya lang, yung x tilde na nakuha ko dito, even if resulted into a very small residual norm, okay, napakalayo niya dun sa initial solution na nakuha natin. Dun sa walang epsilon o dun sa walang noise, ang nakuha natin ay 1,1. Pero dito sa may noise na 1% lamang, negative 3, around 7.2 yung nakuha nating solution. And in fact, that is around 523% away from the exact solution. And you see how catastrophic the effect of the 1% noise is to the solution. 1% lang yung nabago sa right-hand side. Pero 523% yung nangyaring pagbabago doon sa solution. So, ibig sabihin kung ito ay isang, kunwari kung ito ay nasa earphone mo, napaka-konti lang nung mafi-filter na noise. Baka nga makagulo pa kasi 520% yung error o kalayo dun sa actual na pang-cancel ng incoming noise. That's very huge. Okay? Though hindi niya naabot yung maximum kasi ang expected natin, it's about 629. The condition number, 629 times 0.0105. So yun yung upper bound na ina-expect natin na change. Pero hindi niya na-attain. Pero it's still close, right? It's around 523%. So, and that could spell out problems for us. Okay? So, yun yung kailangang i-address ng isang numerical scientist o isang numerical analyst o isang mathematician or applied mathematician. Paano ko kaya mamimitigate yung epekto ng noise doon sa solution? Okay? So, dapat maliit na noise, maliit lang din dapat itong relative error na ito. And the answer to that ay yung ibinibida ko kanina na Tikhonov Regularization routine. Now, anong ginagawa ni Tikhonov method? Ang ginagawa ni Tikhonov method ay, imbis na kunin yung least square solution, yung least square solution kasi ito yung sinusolve. When we say argmin, kinukuha niya yung minimizer nito, right? So yung idea natin na pagsosolve ng linear system AX equals binaging optimization problem. We want to minimize this guy. We want to get the x value that minimizes the L2 norm of the residual. So, yung x na nakakapagpa-minimize netong ax minus b, yun yung tinatawag natin na argmin. So, pag nakakita kayo ng argmin of something, you are looking for the minimizer netong nandito. So, ito yung binibigay sa atin ng least square solution. Siya yung minimizer ng norm ng residual ax minus b. Now, sabi ni Tikhonov, kapag ka malaki yung condition number nung matrix mo, wag mo lang basta kunin yung minimum norm, wag mo lang kunin yung least square solution. Kunin mo yung Tikhonov solution. Ano yung Tikhonov solution? Ang i-minimize mo ay hindi lamang yung residual, ngunit yung sum ng residual squared plus alpha times the norm of the actual solution, where alpha is some regularization parameter that is between 0 and 1. So nangyayari dito ay, okay, wag lang ito yung i-minimize natin. This represents the accuracy of our solution x kasi gusto natin maliit yung residual. Nandito pa rin naman siya kasi gusto nga nating i-minimize pa rin yung residual. Pero pwede tayong magbigay ng ilang breathing room o konting breathing room doon sa solution. Hindi natin kailangang makuha yung may pinakamaliit na L2 norm ng residual. Baka pwedeng pagaanin natin yung burden ng pagkakaroon ng napaka-accurate na result para ma-mitigate yung pagiging ill-conditioned ng matrix. And that's what this second term in the objective function represents. Pababain dapat natin yung norm din ng solution. Because the bigger the norm of the solution is, the bigger its effect on the right-hand side becomes, right? Kasi ax equals b, pag malaki yung norm ni x, ibig sabihin, ang laki ng epekto ng solution dun sa right-hand side vector. So to mitigate the effect, dapat maliit lamang yung norm ng solution. Kaya ang tawag usually sa Tikhonov solution, siya yung minimum norm solution. Because this method tries to strike a balance between the residual or the accuracy of the method plus the size of the solution, which is an effect on the stability of the method with respect to the noise to the right-hand side. Okay? So, ibig sabihin, piliin dapat natin yung balance between keeping the solution as accurate as possible while mitigating the effect of the noise. Kasi mangyayari, kapag masyadong malaki, sige, mamaya na lang pala yun. Mamaya pa pala sa script ko. Pero ito yung gusto nating isolve. Now, there are several problems here, sir. Ang laking optimization problem na. Kailangan kong i-minimize itong sum ng mga functionals na yan. Is that difficult? Well, actually, it turns out it is not that difficult. The solution x alpha that we have over here is actually already solved. Ito na yung closed form solution niya. So yung minimizer x alpha, itong functional na to, nung residual squared plus a multiple of the solution norm squared, ang solution niya lagi ay ito. Okay? It is alpha times the identity matrix of the right size plus A transpose A. Kukunan ko siya ng inverse plus times A star A plus B. And halos kamukha ito nung sa minimum norm solution kasi sa minimum, ng least square solution. Sa least square solution kasi remember meron lang tayong x star equals A pseudo inverse B, and if A star A is invertible, then this is equal to this guy times A conjugate B. All right? Kamukha siya ng solution ng normal equation. Yun nga lang, nagkaroon tayo rito ng alpha I. Okay? Parang binabago lang natin ng konti yung mga nasa diagonal ng matrix A star A. Kasi nga alpha I na multiply lang ng alpha, yung identity matrix. So ito lamang ay diagonal matrix na ang laman ay puro alpha. So yung mga alpha, si alpha ay maliit na number. Alright? So ibig sabihin, binabago lang natin ng kaunting-kaunti yung diagonal entries ni A star A. And the beauty about doing that, nababago yung singular values ng isang matrix. Though I don't want to talk about singular values kasi hindi ko siya diniscuss sa klase, nasa linear algebra yung pagko-compute ng singular values. That's why I would like to request that you accept equation 9.12 without any proof, all right? Just trust me, totoo yan. Ito yung solution dito. Okay? So kung gusto mong mahanap yung Tikhonov solution, ito lang yung gagawin mo. And actually, we can understand this. We know how to compute this guy. So plug in lang to. Diretso kay MATLAB. Ito na yung alpha. Ito na yung x sub alpha. Now, the problem now boils down, what should alpha be? Alpha is a positive regularization parameter na pang-weight doon sa norm ng solution. Now, if alpha is very small, anong mangyari sa alpha? Kung masyadong maliit si alpha, so posibleng lumaki yung minimum norm kasi nagmi-minimize tayo, di ba? Gusto nating paliitin itong sum na to. So kung si alpha ay maliit na to begin with, then this method will allow or can allow the norm to be malaki pa rin. Pwede itong maging malaki kasi anyway, hihigitin naman siya pababa ni alpha. So that means kapag ka masyadong maliit si alpha, ibig sabihin this guy can be as large. At pag malaking norm ng solution, hindi natin nababago masyado or hindi natin natatanggal yung ill conditioning ng problem. So hindi natin gusto si alpha na masyadong maliit. Ayaw din naman natin na masyadong malaki si alpha. Kasi kung masyadong malaki si alpha, ibig sabihin, mafo-force na maliit itong norm ng solution. So ibig sabihin, magkakaroon ng chance na malaki yung residual. Or nabaligtad ko ba siya? Hold on guys. Tama. Kung si alpha ay masyadong malaki, yung solution might be inaccurate. Bakit? Kapag ka masyadong malaki si alpha, so ibig sabihin maprepersa ito to go smaller. At dahil naprepersa to become smaller, there's a chance that this will go large or that will become large. So pag masyado namang malaki si alpha, posible namang inaccurate yung result nating makukuha. So we need to strike a balance between keeping the solution accurate and stable with respect to perturbations dun sa right-hand side. Now, so sir, may balance pala dapat. So paano ko dapat computein si alpha? There are several ways on how to compute alpha. Yung ginagamit ko sa research ko ay Morozov discrepancy principle, which is basically a minimization problem. So optimization problem siya ng isang functional operator. Pero dahil wala akong time na ituro sa inyo yon, kung gusto nyong matutunan, you can enroll in the computational inverse problem class, special topics class that probably I will teach next semester. Sorry, shameless plug. Pero kung magdunumap kayo, I suggest you take that course. Okay? Pero kung merong isang madali, and this is usually used sa engineering. Yung mga engineers, ito yung paborito nilang gamitan kasi napakasimple. Ito yung tinatawag na L-curve. Okay. Ano yung ginagawa sa L-curve? Sa paggagawa ng L-curve, ang ginagawa natin ay nagko-consider ako ng napakaraming alphas. Tapos sinusolve ko yung X alpha para sa bawat isang alpha. And then I record what is the residual norm, tapos i-record ko rin ano yung solution norm. Okay? So meron akong sandamukal na values ni alpha, isosolve ko palagi si X alpha. Tapos kukunin ko, i-record ko sa bawat run ng simulation ko, ano yung size ng residual, ano yung size ng solution. Okay? And then I will plot it in a two-dimensional Cartesian plane. Kukunin ko yung graph neto. Tapos, ang makukuha kong graph, kaya ang tawag sa kanya yung L-curve, ay mukhang letter L. Okay. Tapos, ang optimal alpha ay yung nandun sa corner nung L-curve na yon. Kaya ang tawag sa kanya talaga L-curve. Alright? Now, bakit ito yung pinipili natin? Bakit yung corner? Kasi itong corner na to yung nagbibigay ng maliit na residual and at the same time, maliit yung solution norm. Okay? Kasi kung ito yung pipiliin ko, halimbawa, ito yung alpha na nagbigay nitong point na to ang pipiliin ko. Kung ito yung pipiliin ko, ibig sabihin nito, maliit yung error. Kasi ito yung residual error. Maliit yung error, pero ang laki ng norm ng solution. Ibig sabihin, maganda nga yung solution na makukuha ko, pero ang laki nung sensitivity niya dun sa right-hand side perturbations. Okay? Pag dito naman ako sa kanan kumuha, hindi nga siya sensitive sa perturbation kasi napakaliit ng solution norm, pero ang laki ng error. Yung residual norm is more than 10 to the negative 1. So we are really striking the balance, and apparently that will be obtained in the corner of the L curve. Medyo tricky nga lang ito kasi pag napaplot mo na to kay MATLAB, isa pang question ay paano ko kukunin yung corner. Kasi hindi ko siya makikita kasi yung alpha, ang kailangan kong kunin ay yung alpha ng nagbigay ng corner na ito. So kailangan kong paano nga pala sino yung alpha na ginamit ko para makuha itong point na to. Okay? Kasi yung x component, siya yung residual norm, yung y component, siya yung solution norm. Okay? So if you will allow me, I can say, show you my code for this for the next 10 or 15 minutes. So kung okay lang sa inyo. If you have classes or you have something else to do, you can leave and then just watch the recording later. Pero yun yung idea ng L curve, okay? At ng Tikhonov regularization. So before I go to the MATLAB code, any questions so far? Okay? So kung wala naman, sige, tingnan natin yung code. So, and let's see this through example 9.5. I-solve natin yung system 9.10. Balikan ko lang yung system 9.10. Etong sa example 9.4 natin. So, ito daw yung isa-solve ko. Oops. Ito yung isa-solve ko. And remember, nakakuha tayo ng accurate solution. Okay? Yung accurate solution natin, 0.56% lang yung residual, pero napakalaki nung relative error ng solution, 522%. So we'll try to keep this down while keeping the residual norm a little, probably a little high, kasi napaka-accurate nung 0.5%. Siguro we can sacrifice some of the accuracy. Siguro we can afford to say 5% yung residual norm, pero dapat maliit yung solution norm. Para maliit lang yung effect ng noise, ng 1% noise doon sa solution. Okay? So yun yung gagawin natin. Nag-sacrifice tayo ng accuracy to gain some stability. Okay? So tingnan natin ano nga ba yung ginawa ko rito bago lumipat kay MATLAB. So ang ginawa ko dito ay yung alpha interval ay ginawa kong 10 to the minus 16 hanggang kay 1. Kasi alam ko ito ay isang number na maliit. So 10 to the negative 16 kaya 1, hinati ko yan sa sandamukal na points. Naging OA ako dito, 1 million points yung ginamit ko. Dahil 1 million values of alpha yung ginamit ko, ibig sabihin 1 million times kung kukomputin yung x alpha. And for this example, that's fine because it's just it's a 3x2 system. So okay lang, kaya ng MATLAB ko na mag 1 million iteration, 1 million solutions, ano? Ang step size ay 10 to the minus 6. So sa bawat isang alpha na nandito sa interval na to, makakakuha ko ng isang point na ito yung itsura. Solution norm, residual norm, solution norm. Okay? Tapos ipapaplot ko yan, makakuha ko ng itsurang L. So ang gagawin ko, hahanapin ko tong corner na yan. So yun yung gagawin natin. Let me shift to MATLAB. Kailangan ko palang i-share yung buo kong screen. Kasi may lalabas na figures. So, hold on guys. So, I hope you guys can see my screen now. Tignan ko nga. Kita niyo na ba guys yung screen ko? Hindi siya nag-appear sa akin. Oh yeah, hold on. Ano nangyari? So, ulit. Okay, there you go. So, you should see my screen na. So, punta ako kay MATLAB. Okay. So, ito yung prepare ko na example. So, para sa curve, ito yung gagamitin natin. Nasa na nga ba yun? Okay. So ito si matrix A na ginamit natin. So na-given sa problem. Tapos ito yung right-hand side vector. So dinaya ko lang. A times 1, 1 kasi alam ko yung exact solution ay 1, 1. Pero you could have written here kung ano yung right-hand side vector talaga. Tapos ito yung epsilon natin. Ito yung error vector o yung noise vector. Alam natin ito ay isang 1% noise. So that's fine. Tapos, okay. Tanggalin ko na to. Hindi ko to kailangan yung A minus B. Alright. Mga pang-check ko lang yan along the way. Tapos, tanggalin ko na rin to. Okay. Tapos yung line 11, ito yung nag-create nung alpha interval. Okay? So nag-start ako, gumawa ako ng isang vector na ang laman niya ay simula kay 10 to the negative 16, papunta kay 1, pero yung step size na gusto ko ay 10 to the minus 6. So if you click on this, all right, i-run ko to ng paunti-unti. Okay. So alpha now will be a 1 by 1 million 1 vector. So 1,000,000 yung values ni alpha. So that means I'll need to solve for the Tikhonov solution 1 million times. And that is what is given in line 14. So ito yung formula para sa Tikhonov solution for the specific alpha na nandun sa ating alpha interval. Okay? So I am iterating on it from 1 hanggang dun sa kung ilan yung alpha values. Sa bawat isang alpha value, i-compute ko ito. Ito yung x sub alpha. Pero isi-save ko yung solution norm at saka yung residual norm. Okay? And then after I get this 1 million points or 1 million 1 points, okay? Ipapaplot ko na ngayon yung L curve. Okay? So, itong figure na to, itong line 19, ilalabas nyo lang yung figure na buong screen. Sabihin ko mamaya kung bakit ko gusto yung buong screen. Tapos, ipapaplot ko na yung L curve. Usually, para magmukha siyang L, gusto natin siyang i-plot in a log-log scale. Ibig sabihin, logarithmic yung scale sa x-axis, logarithmic din yung scale sa y-axis. So kaya para powers of 10 yung scaling doon sa x at saka sa y-axis. Kay MATLAB, ang kanyang syntax ay log-log. So ano siya, parang, i-measure niya lang yung x at saka y-axis in the logarithmic scale, powers of 10. Tapos, label lang ng x-axis, label ng y-axis. Tapos, ito yung gusto kong, sorry, yung line 25, ito yung dahilan kung bakit ko gustong full screen, yung makuha na figure. Kasi itong line 25, it will allow me to click a point on the figure that MATLAB will generate. Tapos, isi-save niya yung x at saka y coordinates noong i-click ko na point dun sa screen into the vector xy. Okay? Tapos, kapag alam na ni MATLAB, ang kinlik niya ay yung point na to, ang gagawin ng line 26, itetest niya. Ano yung pinakamalapit na point doon sa, ano yung pinakamalapit na point doon sa collection ng mga solution norm at saka residual norm ang magko-correspond doon sa kinlik ko na point. Kasi posible na yung maklik ko na point ay wala talaga doon sa L curve. Kasi nga, finite lang yung precision ng mouse at nung pagkiklik sa screen. So kailangan niyang hanapin ano yung pinakamalapit na entry doon sa solution norm vector na magko-correspond doon sa value ng solution norm doon sa point na kinlik ko. Kasi rito ibibigay niyo yung xy component, ano? So i-compare ko ngayon yung y component na nakuha ko doon sa kinlik ko na point, pero yung y-axis nagko-correspond siya sa solution norm, ano? I-compare ko ngayon dun sa vector ng mga solution norms, ano yung entry na yon ang pinakamalapit doon sa kinlik ko na y component. So yun yung itetest nung vector na test. Tapos ngayon hanapin ko ano yung coordinates nung point na may pinakamaliit na distance o yung pinakamalapit mula dun sa naklik ko na point. Para mahanap niya pang ilang alpha yung nakapagbigay ng solution norm na pinakamalapit dun sa kinlik ko na point dun sa L curve. Yun yung gagawin ng line 27. So ibibigay niya ano yung coordinate pang ilang alpha. So pag alam ko na kung ano yung coordinate number, kaya ko nang i-computein ngayon yung alpha na optimal ay equal dun sa alpha on the cohort entry noong alpha vector o noong alpha interval natin. Okay? Tapos para lang ma-check tama ba yung na-click ko, ipapa-compute ko ngayon, i-display ko uli yung L curve, pero this time naka-plot na rin yung yung point na magko-correspond dun sa alpha na optimal. Para lang ma-double check ko na talagang yung corner yung napili ko. Tapos ngayon titingnan ko na ano yung X alpha solution at gaano siya kaganda. Okay? So run natin, try natin i-run yung program. Okay. So i-run ko siya, okay. Kukomputin niya yung 1 million solutions. Pinapahiya ako ng laptop ko ngayon, ang bagal niya. Pagbigyan na natin, 1 million yung sinusolve niya na solutions. Bakit masyadong matagal? Oh, there you go. So ito yung L curve na nakuha ko. Ngayon, magte-take into effect yung G input na ginamit ko. So si G input, pag nagpunta ako dito sa figure, kailangan ko lang mag-click ng isang point. At alam ko na yung optimal na alpha na hanapin ko ay yung nandito sa corner. So i-click ko yung something here in the corner. Na-conscious ako pag-click. So ano ba yan yung corner? Okay. And then there you go. Ibig sabihin, nakuha na ni MATLAB. So merong pangalawang figure na nag-pop up. Oops. Hindi ko siya mapalaki. Ayun. There you go. Tapos ibig sabihin, okay, good. Kasi yung alpha na nakuha ng aking G input ay nag-correspond dito sa corner talaga ng L curve. Kaya nakita niyo may orange dot dito sa pangalawang figure na nakuha ko. And then I'll go back to MATLAB para makita ano yung solution ko na nakuha. Well, in this particular case, the optimal alpha that I got ay equal kay 6.47 times 10 to the negative 4. Hopefully kaparehas ito nung nandun sa module. All right. And then the solution X alpha that I got is this one. Okay. 1.0723 and 0.8937, which is close to the actual solution that we expected. Ang expected natin ay 1,1. True enough, if I compute for the norm, X alpha minus X real, ang X real nga pala natin dapat ay 1,1. Tawagin ko lang X real yung vector na 1,1 kasi yan yung expected unique solution natin dun sa unperturbed system. Okay? So, kukomputing ko ngayon gaano kalayo yung X alpha relative to the real solution. So, kunin ko lang yung relative difference. It's 0.0909%. Sorry, 0.0909. So that means 9% na lamang yung naging epekto nung 1% perturbation. So at least on the same level sila, nasa order 1 sila or nasa order 10 to the 0 sila. Kasi 1% na error, nagbigay lang siya ng around 9% na deviation mula dun sa actual solution. And this is way better than what would have happened kasi ang laki 'di ba ng condition number nitong matrix A. Nakita natin na the relative error between the solutions can get as high as around 600%. Pero yung 600% na yon, ang na-attain natin dun sa least square solution ay 522%. Pero with the simple addition of a regularization parameter alpha, bumaba na lang siya sa 9% yung relative error. Okay? Napakalaking epekto pala nung alpha na na-introduce natin. And do we still have an accurate solution? So to find if we have an accurate solution, we need to compute the residual norm or the relative residual. So it's A times X alpha minus the right-hand side vector B. Yung right-hand side vector B dito, ito yung perturbed na B, right? Tapos divided by the norm of the perturbed B, comma 2. So 0.0103. So merong 1% error doon sa solution. So nag-sacrifice tayo. Doon sa least square solution, ang nakuha natin ang relative error, ang residual error ay 0.5%. So pagka pinabayaan mo siya na, okay, magsasacrifice ako ng accuracy. Sige, accuracy, pwede kang umabot ng 1% yung error. So yung sacrifice natin na about kalahating porsyento ay nakapagbigay sa atin ng napakalaking stability. Naging 9% na lamang yung deviation mula dun sa actual solution. Okay? So, do you guys have any questions? Does this make sense? Probably I'll share with you the MATLAB code that I used. All right, so para pwede nyo siyang balikan. So, i-upload ko na lang siya under module number 9 para pwede nyo pag-practicean, paglaruan. Ano? So, ang crucial lang naman dito yung G input, yun lang siguro yung bago. Saka yung pag-extract ng coordinate. So, medyo matagal ko yung pinag-isipan kaninang madaling araw. So, let's go back to the module. Okay. Hold on. Bawiin ko na lang yung sharing sa tablet. Actually, ito yung isa sa mga bagay na natutunan ko nung nagtitesis na ako sa PhD. Hindi ko 'to natutunan sa UPLB, pero parang napaka-amazing niya para hindi pag-aralan sa isang undergrad level na marami namang konsepto ang pwede nating tanggapin without proof, right? So kung MS ka or PhD ka na mag-work sa numerical methods, so saka mo na lang pag-aralan yung mga proofs, pero these are very valuable tools. Lalo na dun sa mga mag-ESP sa akin, di ba, Denmark? Kakailanganin natin to. Kaya isiningit ko ito dito sa ating discussion today kasi malaking tulong ito para sa inyo. So, yun. Meron ng exercise na binigay dito. Under Module 9, meron akong in-upload na MATLAB file na nagko-contain ng data. Ang laman nito ay isang 32 by 32 na matrix, tapos right-hand side vector na 32 by 1. 32 by 1 nga ba? Yeah, 32 by 1. Tapos ito ay ang laki ng condition number nung matrix na to, nung 32 by 32 matrix na to. Pero maganda kasi itong 32 by 32 matrix na to kasi ito ay isang matrix, isang sample problem sa pagre-reconstruct ng isang one-dimensional image. So pwede mo tingnan, meron kang isang image, tapos nag-picture ako, kaya lang blurry yung nakuha kong picture. So ang pwedeng gawin kasi doon, yung pixels doon sa blurry image ay i-transform into a matrix. Tapos ililinearize ko yun. Actually, hindi ko ililinearize. Dapat three-dimensional matrix kasi yung mga pictures. Yung mga RGB pictures, lagi silang three-dimensional matrix. So meron kang row, width, meron kang row, column, at saka meron kang pangatlong dimension o yung height or something or depth. So, pero pwede mo siyang i-reduce into a matrix after resizing. So isa tong example. Itong 32 by 32 matrix na to, parang isa siyang one-dimensional image na kinompress, pero blurry. Okay? Tapos gusto nating i-reconstruct ano yung image pag tinanggal ko yung blur o yung noise. Paano ko makukuha yung pabalik, yung actual picture. So yun tinatry sagutin nung matrix dito sa exercise. So I just want you to explore or to redo what I did with the example. So tingnan nyo lang yung conditioning ng matrix A by looking for the condition number. So kunin nyo lang naman yung condang A kay MATLAB, bibigay niya malaking number. Tapos hanapin yung least square solution. Okay, AX equals B, least square solution. Tapos gaano kaganda. Computin nyo lang yung residual norm doon. Tapos maglagay tayo ng 1% na noise doon sa mag-speculate pa tayo. Kasi alam na natin yung condition number, so alam na natin by how much at the worst case pwedeng magbago yung solution ng perturbed system mula dun sa baseline system. So, pwedeng magko-comment kayo dyan. Sir, katulad sa example natin kanina, alam natin na pwedeng umabot ng up to around 600% yung, hindi pala 600%. Yeah, 600% yung relative error, okay? Between the actual and the noisy solution. Tapos sa number 4, magge-generate tayo ng noise vector. I-add natin to dun sa right-hand side. So sinabi ko rito, bahala na kayo na mag-construct ng generated noise. Mag-construct ng noise na i-add dun sa right-hand side. Tapos kunin nyo yung Tikhonov solution. Kaya lang medyo malaki to, 32 by 32. So pwede kayong magkaroon ng alpha interval from 10 to the minus 16 papunta kay 1. Pero pwedeng bawasan nyo na lang yung number of alpha points. Pwedeng Wag ng 1 million kasi baka magreklamo na yung computer niyo. Actually, kaya pa rin naman siya ng computer ko. Kaya lang nung output ko na sa kanya yung picture and so on, nagbi-beep, beep, beep, beep na yung laptop ko kagabi. Hindi ko matrace kung saan. Galing ba yun sa YouTube na nakabukas o dun sa Spotify na nakabukas o dun sa Netflix na nasa kabilang tab. Hindi ko makita kung saan nagagaling yung sound. So feeling ko nagrereklamo yung RAM ko na mauubos na yung memory ko kasi ikaw ba naman mag-store ng 32 by 30, 1 million matrices na 32 by 32. Pinasave ko kasi may ginagawa mga sanity checks. So, pwede nating babaan. Gawin nyo na lang yung alpha interval na 10 to the minus 3 or 10 to the minus 4. Gagawa kayo ng L-curve, tapos hanapin nyo yung Tikhonov solution with the best alpha according to the L-curve. And I think that's it. So, any questions? So baka yung mga topic ngayon ay isama ko na lang siya sa problem set. Ano? So kasi wala na tayong lab exer corresponding to these topics. Pero siguro a couple of problems na lang. So yan. Okay, so mukhang wala naman tanong. Sayang kasi gusto ko sanang actual picture yung ibigay para masaya yung exercise 9.6 ano. Magbibigay ako ng image tapos medyo may tatago akong message dun sa image ano. So blurry siya, hindi niyo siya or pixelated siya. Tapos ipapa-convert niyo siya kay MATLAB into a matrix. Tapos ang goal niyo sana sa exercise ay ma-reconstruct ano yung image before ko siya binlur o bago ko siya pinixelate. Kaya lang medyo maraming parte yung code na kailangan daanan. Kailangan nating daanan paano i-convert yung picture papunta sa matrix. Kaya lang yung matrix na yun ay multidimensional. Depende kung RGB siya o ano nga ba yung may cyan, yung CMYK ba yun or something like that, yung pakabilang color system. So medyo maraming mangyayari. Tapos integral operator siguro. Kaya sabi ko hindi. Pag nagturo na lang ako ng computational inverse problem, saka ko na lang ipapa-project yan. Okay? So if there are no questions, then thank you guys for putting up with me. Overtime na naman tayo ng 20 minutes. So thank you guys. And then walang lab exer, but remember lab exer 4 is due later around midnight. Then boboto tayo sa Monday ha. So make sure that we get the government we deserve. So then makita-kita ulit tayo sa Wednesday next week. Okay guys, have a good weekend. Bye-bye.